Hey guys, welcome back. What I did was I went and downloaded a couple of data sheets because I wanted to just work out some rough things. This isn't the same display that's in there, but it's the same kind of display. And I just wanted to see what a typical current is that these things get driven at. It looks like it's in the 2 to 10 milliamp range. So, I mean, I wouldn't think you'd drive more than a milliamp or two at the most per piece. I mean, it's being multiplexed, but at the same time, so that and continuous current are two different things. But I want to have a look at that to get an idea of current draw, because there's that and the micro. And then I got the data sheet for the micro. Here it is. Sorry about that. So like I thought, it does have an ADC in it, and it runs at 16 megahertz. So that's what those high frequency pulses are that we can see on the right above the micro when I put my loop antenna over it. But that doesn't really seem to be causing an issue anyway. So I'm gonna do a little bit more reading on this, and I'll get back to you with what I think I am going to do. Okay, so making further discoveries here. The pin that we were looking at the other day that has a capacitor attached to it going to ground that's not the VCC pin is this pin here. It's labeled VCAP. So I'm going to go up in the data sheet now and see how the calculation is done for that capacitor value, because that could be wrong and that could be causing the micro to ring. That's where I'm going to start, and then we'll move our way back to the regulator's capacitors on its input and output, and possibly the resistor value too. And like I said in the last video, I'm not too sure that the ground plane on this board is done properly too, so we'll have to look at that too. So I'll just pause the video whilst I find the part in the data sheet where you calculate the value for VCAP, and then I'll come back. So just before we get to the calculation bit, I've just found that VCAP is for the chip's internal 1.8 volt regulator. It's the capacitor for that. So I imagine that might be for its ADC or something. I'm not too sure. Having a look in the schematic for the board, I don't recall that any of that went to what I thought was an op amp. No, that doesn't go to the op amp. What I will do is I'll have a look at what pin this is that the op amp does go into, or whatever this is. I'm starting to think it's not an op amp just because of the way it's wired up. It's got a snubber network going to ground on this one pin here, and then it's not powered from a reference voltage. Oh, is it powered from the 3.3 volt regulator, is it? Hold on. You know, I don't know if I'd... Shit, there was a kitten on the chair. I almost sat on a kitten. Little kitten. Say hello, guys. Look up. They're very cute. Almost sat on my kitten. Let me just double check. Make sure I haven't made a mistake here. That the output of that regulator does actually feed into this pin here on this device. Would help if I turned my meter on. Yeah, it does. Okay. Maybe there is an op amp then. So let's see. Do we have a negative feedback path? Okay, so we got 3.3 volts there. Ground there. That's the output of the device. That's one input. Assuming it's an op amp. This is tricky. I still don't know that's an op amp. I'm wondering if it's a dedicated part that actually has its own internal reference and comparator and all that sort of thing, or if it's just an op amp of some sort. So I'm just noticing now, okay, this pin's tied to ground, to negative. So we've got negative voltage going in here, and our divided down positive voltage going in on this pin. I just can't see someone getting an op amp running off 3.3 volts, dividing a voltage down, and then just using the op amp as a comparing it against, I guess, the negative rail, and then spinning the value out into a DAC. It doesn't seem quite right, and this snubber doesn't seem right either. I think that is a specialized part. I'm going to go have a look in the data sheet and see what this input is, because that will tell us, you know, if it's a DAC input or if it's a GPIO input, or like what sort of input it is. I'll pause the video and I'll go back to the data sheet, because I still want to have skim through it and find out the calculations for VCAP, and I want to know what that pin is right there. Alright, I'm just going to quickly measure exactly what pin the output of this 6-pin device is on is going into. It's pin 3 opposite the dot. Okay. Pin 3 opposite the dot is PD1 HS swing. Let me think about that for a minute. I'm going to have to scroll up and see what that actually means. So PD1 HS in brackets / swing. PD1 / swing is the swim data interface. Yeah, like I've pointed out on my channel, I'm an analog guy. I am into analog electronics, not really digital, so I understand a little bit. You know, I do know what an SPI bus is, I know what UART is, I know what serial is, but there are other things I read, like I actually don't know what this is. Swim data interface. So I'm scrolling up the data sheet back up a little bit to try and see if I can work this out. I'll just pause the video again to save you guys from waiting on me. Alright guys, I'm back. I didn't have to go far at all. I literally just went to Google and typed in what is PD1 in brackets HS space swim, and I found out the swim protocol is a single wire interface based on asynchronous high sync 8 mA open drain bidirectional communication. So what that basically means is this device that I thought was an op amp is spitting out some sort of bidirectional data into the microcontroller obviously referenced to ground. So that's not an op amp. So I was right when I saw the snubber on one pin going to ground and the way it was set up. I was starting to doubt it being an op amp, so it's obviously not an op amp. I'm going to pause the video again and see if I can identify this part. Because it's a 6-pin device, it's obviously some sort of voltage analyzer sort of device. So I'll see what I can come up with and I'll come back. Just something else that I wanted to point out. The reason why, even though I've basically knocked out all the oscillation, I'm still going to play not just with the regulator that and its capacitors and the VCC cap for the micro, the main voltage cap, on the, you know, that decouples the positive terminal to ground close to the micro, and then the bulk cap near the regulator, and maybe even my input cap. But the reason I'm still going to play around with the other capacitor value is because here's the thing, right? If this thing's oscillating, it could cause non-linearity in the way it measures and displays voltage. What I mean by non-linearity is, I don't know if you recall in previous videos, like it was bang on accurate from 0 volts up to about 12, and then from 12 to 30 volts it would develop up to a 25-30 millivolt error. I then changed R1 and R2 on the divider to precision resistors and then trimmed them with even more resistors, and I got it even more accurate from 0 to 30 volts, but now it's not perfectly accurate anywhere. So when it's turned all the way down, I think it's 1 millivolt out, and when it's turned all the way up, it's 2 millivolts out. But I think it goes in the opposite direction. So like when it's all the way down, it's 1 millivolt too low, but when it's turned up all the way at 30 volts, it's like 2 millivolts too high. That's what I mean by non-linearity, and all this oscillation could be causing that. So it's all well and good to be like, ah, it's good enough, you know, whacking in. No, because, you know, if it's not bang on perfect, that oscillation could be playing with it and affecting the actual precision of the device. So anyway, like I said before, I've got a little bit of research to do on these 3-terminal regulator devices, CMOS based ones, particularly the 71XX series. I'll be back in a moment. I just wanted to point that out because, like the thing that I showed you with the series pass transistor not being able to have a reverse voltage on it, I thought I should point that out too, because it's just another trap for young players, you know. Like, you could design a circuit that's got a micro and an ADC in the micro and an external voltage reference, or an internal one, and some regulators around the board and op amps and different things, and have a few millivolts of ripple on there and be like, ah, that's only a few millivolts of ripple, that's fine. Or noise, or oscillation, or ringing, or whatever it is. But what you don't know is that's actually leaking into your microcontroller, your op amp, and all of these different devices. They've got different common mode rejection ratios, power supply ripple rejection ratios. So what that means is they all leak a little bit of that noise inside them, into your measurement. So yeah, you know, and that can cause non-linearities, especially if the noise is like not so much non-sinusoidal, but an uneven waveform. So if the waveform's got like more negative going halves with bigger pulses on the negative half than the positive half, for example, you know, that could cause values to read too high or too low. That's just an example. Like, all sorts of weird things can happen just because of ringing in a circuit and noise getting into microcontrollers and ADC inputs and op amps and stuff like that. But I just wanted to point out that we're not just getting rid of the oscillation because it's a problem with it going back into the emitter of my comparator transistor, but we also want this circuit here to behave to its optimum capacity as well. Alright, I'll be back in a moment. So what I'm going to do, I've just going to grab the 10 microfarad at 25 volt tantalum, and I'm currently looking at the output rail. I'm just going to stick this guy just across this cap first on the output of the regulator. Yes, the waveform got literally half as small. Okay, that's good. That's good news. We'll just short that out. Now what about the one that's closer to the micro? Actually has the same effect. You'd think it would have more of an effect. So apparently me upping the capacitor that was there originally, which was 100 nano to 1 micro, that's done all the job you can do for getting rid of the high frequency noise that was just around the micros positive line. This bulk capacitor, I'd say the noise goes away by half by adding another 10 microfarads. So what I'm going to do is I'm going to take this 10, actually I'll leave it there for now. I'm going to go grab a 22 microfarad. Oh, I've only got 22 at 16. What else have we got? Okay. I know this is probably not going to work. I just want to see if I put a 22 microfarad electrolytic across that, if that will make it even smaller. Somehow I don't think it will because of the lack of high frequency response. Oh, I thought I just killed my regulator. Yes, I was going to swear and say, fuck. I thought I just killed my regulator. I didn't. I just pulled the power wire out the board. Okay, the electrolytic, as I thought, its ESR raises way too much with frequency and it's just not even having an effect. So I'll put that back away. Let me just have a quick look through my scrap boards and see if I've got any tents that will help in this situation. I'll be back in a sec. Okay, so I don't actually have any tents that are useful other than a whole load of 10 microfarad ones. I've only got one single 22 microfarad that's at a higher voltage and some other values. So I'm definitely going to need to order some tents. So what I'm going to do in the meantime, because in my SMD boxes I've got a whole load of these capacitors. So I'm going to go get my LCR meter, go over and find the same type of ceramic capacitors. They come in different types and values and voltages. I'm going to find the same type with the same frequency response, 10 microfarad ones. And I'm just going to make a sandwich 3 or 4 high to effectively make this ripple smaller. And I'll just show you guys quickly what happens when I stick this tantalum capacitor over the rail. That's the ripple on, the output of the LDO. And that's with the capacitor. Without the capacitor. So it's a 10 microfarad capacitor that's already on the board, and that's with me adding a 10. So obviously adding another 10 or 22 or 33 it'll make that ripple almost non-existent. So, oh yeah, and I did a bit of research on it, and it looks like these devices can handle a bigger capacitance on the output. There are some case scenarios where they can't, so what I'm going to do just in case, actually, the thing it's being powered off of has got the 470 mic cap on the output, but it is powering relays. So you know what, just to play it on the safe side, I'm going to put a diode pointing back across the regulator, so that on power down, when I put 47 microfarads of capacitance there, I don't get a reverse breakdown voltage through the regulator. So I'll go do that now. I'll go grab a 4148 diode, 1N4148, and another 3 10 microfarad capacitors, and I'll be back in a sec. Okay guys, so I've grabbed these 4 10 microfarad SMD caps. These have got the same properties as this capacitor in terms of frequency response and ESR, except for better ESR because these are a higher voltage rating. So these are the capacitors that like to go up above 100 kilohertz, up into the megahertz range. Not that that's really critical there like it is for the VCAP, for the internal voltage regulator, but it's still fairly important, so I chose the better quality ones. And there's 4 of them there. I'm not going to stack them on top of that one, I'm just going to take that one off and replace it with those 4. So I'll do that. VCAP, you know what, I'd like to look at VCAP quickly before I do that too. I think what I'll do, again, I'll grab this tan. Oh no, it's 10 mic. Let's grab 1 microfarad monolithic, and I'm just going to sit that across VCAP whilst observing the scope and see if it cleans the waveform up anymore. No. So it appears VCAP has no effect on it, so that's good, so I can leave that one. Looks like the only 2 capacitors that are going to be staying on this board's the 1 microfarad VCAP and the 100 nanofarad cap that's on this snubber network. Well, actually, let's have a look at that snubber network and see if there's any noise on that. Oh wow, there's actually a terrible noise on it. Like, terrible. $665 millivolts RMS. Oh, I see what it is. It's data. Okay, so that's actually that's compensation for the data output. And the reason I know that is because I've actually put the scope on the data output pin and had a look at the data waveform. And I'm seeing the same waveform on that. So I won't play with the value of that because that's most likely perfect. I can see like a snubbed waveform that's a little bit smooth, but it still has sharp edges and the right rise and fall time to make it look like a good square wave transitions. So I'll leave that as it is. Alright, well, I'll take that off, stack them on there, and we'll go from there. Soldering iron's gone to sleep. Bench is getting very messy too. Just put all this other stuff I'm not using now away. Otherwise my bench gets very cluttered very quickly. And also having too many bits of wire and metal and components lying around, eventually you power something up and it touches something, it goes bang and whoops. And that's never a good thing either. Just going to put this tantalum back away since I'm not using it. And don't worry guys, I am making a few orders online and a trip to JCar, and I'm stocking up on a few parts I'm running low on. So there's not going to be any shortage of parts. There never is in this workshop. I've been collecting parts for years and years and years. To the point that I've actually at one point removed parts or threw parts out, like discarded parts, because I was getting too many things. So I downsized my collection. Not downsized it, but you know, like I had lots of board pulled parts. I had brand new parts off too, so I threw away like a lot of the board pulled ones that had, say, older looking pins that were oxidized or too short of pins. You know, I had some random parts that were basically unidentifiable, and I got rid of a lot of those. Just random crap that's built up over the years. You'd be surprised how much stuff I've got rid of, and I've still got all this stuff in here, so yeah. These caps, the solder on the side of them just looks so dull. I don't know what on earth they came off of, but we can fix that. Alright, that's that guy on there. So we need two of these caps, three, yeah, two are clean and two are dirty. Okay. Oh, I see, it's just the side, they're all the same. Okay. Let's tack that on. So you see what I mean about stacking them up. So the good thing about stacking ceramic capacitors, or any capacitors for that matter, is every single one that you put in parallel, you're reducing the equivalent series resistance, not just doubling the capacitance. It's almost like building a super cap, kind of. It's not exactly the same as a supercapacitor, but I mean, you could theoretically build a super cap out of a whole load of small capacitors that've got low ESR and then hook them together to form a capacitor that just wants to charge and discharge like almost instantaneously, but it'd be a pretty fucking strange waste of time. My capacitor tower. It's not in the way, is it? I've had a habit of doing that. I hate it when you have to take too much heat to these little guys because they don't like it, but these ones are really dirty and oxidized, so I didn't really have a choice. All I can really do is just cool them off as quick as possible and check them for shorts. They're not shorted, that's great. Should have about 40 microfarads. There you go, 47 microfarads. That's because my multimeter is not an LCR meter and it's not testing right. It's actually 40 microfarads at high frequencies. So let's have a look at our output rail now and plug it in. Huh, that is amazing. Wow. Just to show you guys, I don't think it's going to get any smaller than that actually. That's down at 50 millivolts, 100 millivolts at division like it was before. Yeah, okay. Really impressed with that. Let's have a look at our input now. We're going to have to turn the voltage all the way down. Yeah, so at 5 millivolts at division, it's still exactly the same. That hasn't changed. Alright, well, here's what we know. I just want to see we've only 2 capacitors stacked up. What the ripple rejection's like, because if it really only needs about 20 microfarads, like just double 10, because I just want to point out, when I grabbed a 22 microfarad or a 10 microfarad cap and added it to it, it made the same difference these four did. So I've got a funny feeling that maybe it just needed to be doubled in capacitance to get to where it was. So we'll just check that quickly. Yeah, back to 100 millivolts. Yeah, that might even be smaller. I think that's the sweet spot. I really think that's the sweet spot, 20 microfarads. So I'll keep these two other capacitors here with these parts. These parts are for my power supply stuff that I'm in the middle of doing. I'll leave them there so that I can put them on the other board. I already know what the deal is with the other two capacitors, which ones I'm going to leave and which ones will be swapped for monolithics. It's only a 470 nano. So I'll leave those there and they will go on the other panel meter. Alright, we have one last thing to be concerned about. And we are done. So, just so you guys can see what I was talking about by stacking capacitors. It's just two surface mount capacitors, bigger form factor, just stacked on top of each other. Yeah, my handiwork has got very tight, close tolerances. A lot of people would not be able to do this without just ripping pads and just screwing up the entire board, especially how long I've been playing around with it. But when you've been doing this for years and years and years and years and years, you just get the knack. Sorry, Paws, you can't be up here. Get down. Down. Thank you. You just, yeah, you get used to it. Anyways, we've got 20 microfarads on the output. I'm tempted. What value was that capacitor that was 10 microfarads? This wasn't. I'm just thinking I might be able to reuse the 10 microfarad surface mount. I'm sure that was it. Yeah, that's the one. High frequency responding. 10 microfarads, that's the one. Alright. So what happens if I just literally tack it across our positive rail and our ground point there, effectively giving a 1 microfarad monolithic cap and a 10 microfarad ceramic to bypass the power rail coming in. I'm just going to give it a shot. Why not? That is beautiful. That could not have come out better. You guys got to have a close-up look at this. It's a work of art. Alright, so this will probably be my final test. I'll probably be happy with it now. 12.333 just to show you that it hasn't broken. Oh wow. Oh wow. So at 5 millivolts of division again, it's still just how it was before. It hasn't changed. Hasn't gotten any better. Let me move my ground clip a bit closer. Okay, so it's a bit smaller. Alright. Alright. Let's try tip and barrel this. Get rid of this ground loop. Let's see what I did there. Let's try and get the barrel on there. And the tip on there. Yeah, that's actually pretty close. I'm happy with that. It's about 3.5 millivolts RMS. Just for the record, it was literally hundreds of millivolts before. Hundreds. At one stage volts, but that was my fault. It was bad. Yeah, I'm happy with that. Honestly, I don't think that capacitor I just put on this made any difference at all. What it's going to do is just keep the screen on longer. Doesn't even make a difference to that. I'll leave it anyway because it's 20 microfarads on the output of the regulator and 11 on the input. That's fine. I'm happy with that. I'll go get that diode and I'll put the diode across the regulator just in case, like I said. Actually, the diode will go across those capacitors because they're on the output of the regulator. For this, I'm going to use a surface mount diode because I can just pick the power diode that will sit right on top of the capacitor. M7. There we go. This is just the equivalent of a 1N4007, if anyone's wondering. And we need it to be pointing that way. Okay. This is the diode I was talking about that will stop any over voltage on power down from the bigger capacitor on the output side from coming over to the input side and damaging the regulator. Okay. Right, if I just put that I did, didn't I? Oh god. Guys, there's a possibility I just popped that regulator because I put the diode around the wrong way. I wasn't thinking. Those capacitors go across the output to ground, not the output to the input. This diode's not going to help there. Usually these things have got short circuit protection. It's only running off 12 volts, so hopefully I didn't just pop the regulator. No, we're still alive. Okay, good. Right, so our diode actually, it does get soldered to this side. Should be better off going this way. Okay, and the other side of the diode I want to connect to the input of the regulator. I'll just do that using a piece of scrap resistor lead. I got copper wire too, but it's expensive using tin copper wire, and it's thicker too. I don't need that thickness for this short little run of something that has maybe 10 or 20 milliamp peaks on it in the worst possible case scenario. So I know this has gone on and on and on and on and on, this video series on this. I was not expecting to have any problems with this device. How am I going to do this? Oh yeah, perfect. That works nice. Okay. I'm perfectly happy with that. So there you have it, guys. There is two caps stacked there, and now a diode pointing from the output back to the input. So on power down, we can't risk damaging our regulator. I'm just going to check one more time for ripple in case that diode has formed a path for something that we don't want, but no, it's all gone. It's great. Alright, so that's it. That is the panel made oscillation problem finally solved. Only took me like 2 days. Alright, I'm going to pack this up. I'm not going to do this to the other meter today. I'll do that in my own time, because you guys have already seen the video that I did on, what do you call it? The resistive divider to get the panel meter accuracy better. I've already done a video on that. So I've now done a video on this too. So I won't bother doing a video of me doing the same thing I just did to the other one, because it's going to just be straightforward. Now I know what value components go in. I literally just have to put the same components that I've done here on the other one that's in my power supply, and vice versa for that one. That one needs the same resistive divider that my other power supply has. Well, I know that was a little bit long. Where did the second one come from? Strange things happen in my lab, I tell you. The weirdest thing is they're off slightly different probes. Okay, that doesn't belong there. Yep. Alright. Alright, thanks for watching, guys. You take care. I'm going to pack up, and then I'm going to start filming a series on components, because someone asked me to do a series on components. So that's going to be coming up. I'm going to film the first episode of that tonight, and then we'll do basically more and more complicated episodes where, like I said before, we'll start off with basic components, and then we'll move into the different types of components and how their different properties affect their function, so to speak. So if I sound a bit confused, it's just this extra scope probe clip that I have picked up, and I've been looking at all my scope probes and I can't find one without a clip, so that's a bit confusing. Anyway, you guys have a good night, or good day wherever you are in the world. See ya.